Hey folks, one of my students launched a rocket, one of the larger rockets, that go like 1,000, 2,000 feet in the air, and they had an accelerometer slash gyro. I actually forgot to plot the gyro data. They had a gyro and an accelerometer on the rocket, and they asked me if it was possible to sort of, you know, autonomously take that launch data, which is this acceleration, and like integrate it twice. And I said, well, that's a pretty complicated problem. And I had a meeting with them and basically made a list of like everything that you needed to do, and here's the list. And so I'm gonna do what I always do and just kind of stream of consciousness, just work through this video and see if this is possible. NASA does this with their fancier accelerometers, and you can even get some accelerometers that have that actually integrate. Like the software is already embedded in the accelerometer itself, and the entire chip just spits out position. The problem with integrating acceleration and angular velocity even is that you end up integrating the bias, and so without having sort of like a sophisticated common filter on board to sort of estimate what that bias is, it's really hard to do this. Now, a common filter requires multiple sensors. You can't just common filter like one sensor, because what you need for a common filter is like a model and a sensor, and then you need some sort of truth measurement to sort of tell you that your model is wrong and your model needs to be more accurate than your sensor. And so like you need sort of this play between the two. Um, there's ways to sort of get around that. There you can use like there's like an AHRS filter that you can throw in there. I put in here that you can use like you need to run some sort of common filter. But I basically put like RK4 integrator with like linear least squares estimator because I was trying to basically point out that maybe you can do something different. Number four might be like a follow-on video or something like that. Maybe in this video, like I'll just integrate twice and see what happens. Um, the other idea that we were thinking is that in order to integrate the bias, is if he only had one accelerometer on there, but maybe if you had like 15 accelerometers on there and you recorded data for all of them and then averaged them all together, maybe that would like cancel out the bias. So I'm gonna just since I only have one data stream, I'm just gonna read in the data stream twice. And so I'm gonna say for file and files, load the data. Here's the data here times the first column, and then you've got acceleration x, y, z, and then gx, gy, gz. I think I don't actually know how this thing is oriented, believe it or not. And so we probably need to look at the data and see exactly how that works. I probably should put like a legend on here. So let me grab gy, data all comma 5, gz, data all comma 6. And then let me put a legend on here, label. So this is AX, label AY, and then label AZ. And then I don't want to put the gyro data yet because I don't really care about it. So step one is open the file and read in all the data streams. So that's basically what we're doing here. Step two is we have to truncate the data to be within the launch window. And something that I didn't realize until like just now talking with you guys is we also need to figure out like which direction is what, if you will. So basically, like if you look here at this section of data, this is clearly I turned it on and I'm like shoving it into the rocket, putting the nose cone on, and looks like that took 600 seconds, so like 60 minutes. Sorry, 60 seconds, 10 minutes. And not only do you have to like shove the accelerometer like in there and put the nose cone on, but you also have to get it on the launch pad. And then clearly here it's like just sitting there. This looks like wind, honestly, just like wind rustling. And then it's pretty clear. I mean, this is the highest acceleration. Like this is the launch. So I'm thinking the rocket is like on its side, and that's why it's experiencing, you know, G's in this direction. Oh, and I forgot to turn on the legend. I like put the labels, but I didn't say like, hey, give me the legend. PLT is legend. Um, all right, so let's take a look at this again. So yeah, so AZ, right, is so the rocket's on its side, so it looks like the accelerometer is like this, and the Z component is down. So there's like Gravity is pulling it down. It's under 1g acceleration, and then boom, it accelerates like crazy. Now the interesting thing, of course, with this is the accelerometer clearly saturates. It's flat here, and that's not, you know, it's not like the rocket just accelerated constantly for that. Like that's clearly like the accelerometer is saturated. So if we integrate this thing, we're going to run into that trouble anyway. But we're just going to kind of do what we can. So then basically that looks like a 3 second burnout, which makes sense. These hobbyist rocket motors like burn out after about 3 seconds. So there's like a coast period here where it's basically just it's the acceleration is basically zero. So it's just constant velocity, and it looks like there's a little bit of negative there, just like slowing it down with aerodynamics. And then this is probably like when it flips over, and then this huge spike is probably the ejection charge. Nose cone blows off. And this is just like the insanity of that nose cone shooting off. And here, you see that the AZ direction is now negative, and so that means it's under free fall now. So it's coming down. So here initially it's like on the launch pad just sitting there. But it also looks like it is under free fall, but it's also like upside down. And so that's another concern that I have. Like when that nose cone, blows off, boom, like the orientation of the rocket changes. And then here's a large spike here, right, where it clearly hit the ground. Again, that's a huge spike. That seems kind of odd. And then there's this sort of dead space here, and so that's obviously it's just sitting on the ground. And again, this is again what concerns me is that you notice that like when it hits the ground, it's not in the same orientation. So that accelerometer, like it might be like this when it's on the ground, or even upside down, and it shoots up. But once it gets to apogee, it starts to flip around and do all this craziness, and so. That's a little bit what I'm concerned about. And then obviously it looks like, it hits the ground, and then someone goes and gets it and picks it up and maybe looks at it, takes some pictures, I don't know. And then this is probably like running back, and then they finally turn it off. So what we need is we need sort of an autonomous algorithm to detect when launch happened and then when launch ended. So what I'm going to do is basically I'm going to find, I think it's pretty clear that all of the events happen when it's over 30 seconds. I mean, over 30. I might even say over 35 just to get rid of this spike here and just look at these. So what I'm going to do is I'm going to plot the norm here. So instead of plotting the acceleration like this, I'm going to compute the norm. So I'm going to say just A is square root of ax squared plus ay squared plus az squared. And then that didn't do anything. And then I'm going to plt.plot time comma A, like that. And then we should see, yeah, there we go. This is essentially what I wanted to see. So there's the initial spike there. That's the ejection charge. And then this is when you hit the ground. So what I'm going to do now is everywhere that we see everywhere that A is greater than 35. Wait, hang on. The norm might be different. Let's take a look at this again. Yeah, I think we can say 35. That's fine. So we're going to say, I'm going to say events. I'm going to say time events. So this is where we truncate the data to be within the launch window. So let's grab that. So the time events are everywhere that A is greater than 35. And then we're going to say the A events are everywhere where A is greater than 35. Okay. And then I'm going to plot the time events and the A events with blue stars. I think I can do that in Python. Yeah, hype. Okay, so clearly the events are here. You know, there's like 5 events, okay? Now the question is which one is which? Well, I'm going to assume that, you know, T launch is obviously the first event. But what I'm going to do is, you know, I'd like to grab the data point before it though. So how do I do that? So T launch gives me the time. And let me print. Oh, I have an idea. Yeah. So I'm going to say time of launch equals T launch. Okay, that's fine. And then let me see that got that right. So it's 874. So that's like there, yeah, 874. And then, I mean, should I just grab? That's probably a good idea. Just if you grab the last one. No, well, see, yeah, I think that'll be fine. Just grab the last one. So T land is time events minus 1, right? And print, you know, time of landing equals T land, okay? And so, you know, T launch is at 874 and T landing is 918. So then what we can do then is we can truncate the data at those times. And so we can say, you know, time truncated is time where time is greater than T launch and time is less than T land. Are we allowed to do that in Python? No, it doesn't like it. Can I do two lines of code? Okay, yeah. So I'm allowed to do 2 lines of code. So then so what I really need to do is I need to make a function, because I'm gonna have to do this a lot, and say def truncate, and I'm gonna say give me the vector, give me the s and the e. So that's the start and the end. So first you're gonna say so vec equals vec where vec is greater than s, and then you're gonna say vec equals vec where vec is less than e, and return the vec. Okay. And then basically what we're going to do is we're going to say time truncated is, and then what I want to do too is I want to get rid of this plot here now, because that was just like, that was like a helper plot, you know? And I think there's another plot here. Okay. So time truncated is truncate. Is that the name of the function? Truncated. Let's do truncate. It's an action. Truncate, so I'm going to give it time, T launch, T end, and then I'm going to say AX is AX truncated. I'm going to just do new AXT. That'll be easier. Is truncate time, comma, T launch, T end, T land, sorry. And then I'm going to go ahead and plot time T and X T and see if that worked. That looks terrible. Well, that's AX. Time looks good. Oh, that's because I did time, dude. Duh. All right, let's try again. Oh, boy. Oh, no. Dude. Okay. You need an out vec, and you need a time vec, and you need a T start and a T end. And you need to do all the other vectors first before you do time. Otherwise, it's not going to work. So you need to say out vec is out vec where time vec is greater than T start. And then out vec is out vec where time vec is less than TE. Because if you shrink the time vec, everything gets messed up. So you need to keep the original time vector, truncate everything else, and then truncate the time vector. Okay, so that changes things. So we're going to have to put this up here. And we're going to do AX. Yeah, that's fine. We're going to do AX and then time, and then T launch, T land. And then we'll truncate time. And in this case, we'll give it time twice. And then that should be okay. Blast. Blast. I'm having trouble with this truncation here, bro. Outvec is outvec where timevec is greater than TS. And then outvec is outvec where timevec is less than TE. Oh, do you need to truncate everything at the same time? Yeah, I think you do. So you're going to get timevec underscore is timevec where timevec is greater than TS. Because you need to make sure they're the same sizes. It's going to be a little bit repetitive, and then you put an underscore there. Oh my gosh. Geez, that was ridiculous. Okay, so there's AX. And so now I can do AY, AZ. Okay. Oh boy. AY, AZ. Oh, AZ. And then we can plot AY and AZ and hit go. I didn't like it because I didn't change these. There we go. Okay, cool. Oh, okay, so this is what I wanted to do. I wanted to grab a couple seconds before and after. So I wanted to grab like 1 second before and then like 1 second after. +1, +1, +1. That way there's like a little bit of like, come on. Oh. There we go. Okay, cool. So we got a little bit before, then boom. And then a little bit, yeah, well, obviously that's the same plot because it's the same thing twice. Okay, so we've truncated the data. We need to do the same thing for GX, GY, and GZ. So we're going to grab these, and we're going to GX, GY, GZ, and then we're going to change these AX, AY, and AZs to GX, GY, GZ. Okay. All right. Now we're going to low pass filter the data to remove all high frequency content. Okay, so I wonder, I mean, do we actually have to? Data seems fine. There's a little bit of high, I mean, see, like this just seems like trivial. Like all this like vibration here, I feel like we should get rid of that. So yeah, so let's do a little filter here. So we're gonna say like AXTF for filtered is a filter AXT, comma, and then we need a filter constant. We need like a tau. Wait, we can do this here. Wait, did I? Where did there it is. Okay, I'm gonna copy this and put it. Oh my gosh, here. Basically saying we are going to low pass filter the data. So we're going to say AXTF is filter, AXT, the truncated data, and we need a tau. I'm going to do 0.5 for now. We can change that later. That's our filter constant. And I'm going to go ahead and label these again. I don't know why I just deleted that. I'm sorry. So this is AXT label, AYT, and then label AZT, like that. Okay, seems pretty good. We need the filter function. So def filter. We're going to have the vec and then tau. And we're going to say, so we need our out vec to be 0 times vec. We're going to create an empty array. We're going to assume that our out vec of 0 is equal to vec of 0. Then we're going to say for x in range 1, the length of out vec, of vec. And then we're going to say out vec, oh, and we got to do minus 1, I think. We're going to say out vec of x is equal to, and this is where tau comes in, 1 minus tau times out vec of x minus 1 plus the vec of x. That's a complementary filter. And then I'm going to return out vec. Cool. Let's see if that works. So now after this, I'm going to plt.plot time t axtf, label this axtf, and see what happens. Does it throw an error? No. Okay, so yeah, so that it's hard to tell what the heck is going on because I didn't turn on the freaking legend. plt.legend. Okay. Maybe yes. Okay, so the red line is the blue line filtered. We did something wrong. I mean, that's like bigger. Yeah, something. We broke something. Oh, dude, duh. We forgot to multiply by tau over here. There we go. I need to get my complementary filters straight. Okay. Yeah, there we go. Boom. There it is, lagged and filtered. So the question is what are our edge cases? So if I make tau equal to 1.0, do I get a flat line or the same line? Okay, so 1 is the same line, so that's like no filtering. Okay, so 1.0 is no filter, and then 0.0 must be like over filter. Yeah, 0.1 is like, wait, did I say 0.1? Oh, I did 0.0. 0 should just be a flat line. Okay, cool. All right, so then that means, and 0.0 is over filtering. Okay, so I'm going to do 0.2 just because it seems pretty good. All right, and that will, see that filtered out, I mean, I want that high frequency spike. That's too much, so let's try 4. I want to get rid of all this nastiness, but I still want like these high frequency spikes. That's not bad. I think honestly 0.5 was pretty good. All right, let's filter the rest. So we're gonna do AY, AZ, and then GX, GY, GZ. I'm assuming that the gyro has, I know I haven't plotted it, but I'm assuming it's the same. AX, AY, AZ, GX, GX, GY, GZ. And then let's just plot the filtered signals for the accelerometer. AY, AZ. Let's see. All right, hype. All right, yeah, so I mean, this is another thing. Like it filtered this out too, which we don't really want. But I mean, what I'm really looking for is all of this. I mean, that's what I was saying. Like maybe the filter is not pointed on. I mean, the filter's there. I mean, that just, it's there so that you can use it if you like. Okay, so now we've got filtered signals. Okay, so number 2 is done. All right, so this is the one that kind of scares me. So translate the Excel data streams to numerous center of masses. Okay, so this is the problem that I'm having, is that if you look at the data, right? Oh boy. The accelerometer is clearly on in a certain orientation, and then when the nose cone splits, it is now falling at a completely different orientation. Okay, folks, I space out for a minute because the problem is that when you have this projectile, you have all your accelerometers in one spot, but the center of mass is probably at a different spot. And so whatever acceleration you're reading, you really need to translate that to the center of mass. The problem is that when the nose cone pops off, right, and you burn fuel, the center of mass changes. I honestly don't think I spaced out because I don't think this is possible. I think it's impossible to know exactly where the center of mass is unless you're like building a simulation and you like simulate the fuel burning and then the nose cone popping off. And that's like a huge, I mean, dude, that would take me like 2 months to like, I would have to like write the simulation and then simulate the rocket and compute like the theoretical center of mass for the entire sim. Like, I mean, I don't want to do that tonight. I'm going to skip this one. Skip this one and assume the accelerometer is at the center of mass. And just, or we integrate the acceleration at the accelerometer point rather than CG, which I guess we're just going to have to do. Okay. 3.5 is we average all the streams together. This will remove the bias. Okay, so what we need to do is we need to make at the top of this for loop, we need to make in like AX AVG, and then in AY AVG. No, we don't need to do that. What we need to do is we need to say if, yeah, that's fine. Okay, I changed my mind. AX AVG is boop, AY AVG is boop, AZ AVG is boop, and then GX AVG. By the way, boop is open bracket, close bracket, if you didn't know. GZ AVG is this. Okay. Then what we say, if AX AVG is empty, can I say that? Is empty? No. I'm just going to say if len of AX AVG is 0, then obviously AX AVG. Oh, dude. What if the data streams are different lengths? Oh my gosh, this problem is starting to be ridiculous. Oh my goodness. These two data streams are exactly identical, so obviously it's easy. But if you were truly going to average them, what you would need to do, okay, so you either assume that all the data streams come in at the same rate and they're taking data at the same time, or if there's different timestamps, you'd have to interpolate the different data streams. I'm going to assume that all the data streams are the same because I think my mind is going to explode if I think about that other problem. I'll cross that bridge when I get there. Okay, so AX AVG is equal to AX TF, and then AY AVG is AY TF, and then AZ AVG is AZ TF, and then GX AVG is GX TF. GY AVG is GY TF. GZ AVG is GZ TF. Otherwise, AX AVG is plus equals AX TF, AY AVG plus equals AY TF. Ooh, okay, that's fine. And then num vars is 1. And then we say AZ AVG plus equals AZ TF. GX AVG plus equals GX TF. And copy and paste this 3 times. I don't know why I didn't do that before. You guys are just watching me code this, and you're like, dang, this is boring. Dr. C's getting slow. It needs to be fast. Num var is plus equals 1. Okay, there we go. And then at the end of the day, once the for loops are done, and we can plot, that's fine. Once the for loops are done, we actually compute the average, which is we say AX AVG slash equals num vars, right? Because we have to divide by the number of variables. And then do the same for AY and AZ. And then boop, 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 and then do the same thing for GX, GY, and GZ. Okay, and then what we can do is we can create a new figure. Excuse me. And we can PLT figure, grab all that jazziness. Oh boy. Okay, and then plotting. Yeah, I want to plot these. And we'll plot these, except instead of it being, should we average the time? That doesn't make sense. If the times are the same, we should just be able to grab time t and ax avg, ay avg, and then avg. And I'm going to put acceleration average, and then ax, ay, az, and then that plt.show needs to be here. So we should see n+1 plots, n being the number of plots. So there should be a figure 3, which is just the average, acceleration average, boom. Okay, so there's our filtered averaged acceleration data, okay? All right. So now comes the even trickier part. Okay, so need to run some sort of common filter, RK4, to obtain quaternions and org angles for the entire duration of the flight. Okay, what I want to do is I want to run the AHRS filter. That is in here somewhere in my fast kit. It's a C++ hardware IMU AHRS. Yes, this is what I want to run. So I want to convert this. Is this even a good idea? Run this. Oh wait, I don't have magnetometer data. So I got to do update no mag. So update no mag. Here we go. Boom. I'm going to come run this and pray that this works. Okay. V. Oh boy. All right, let's see if I can convert this to Python code. Okay, so obviously this goes away. Those are floats. Okay, so this needs to be a loop. Okay, so what I need to do is I need to say for x in range 0 to len of ax avg. Okay, and then basically say, okay, look, so it says, wait, why are my tabbings not working? Oh, it's because there's a semicolon there, maybe? Okay. And so I need to say, okay, ax is ax avg of x, ay is ax avg of y, az is I'm losing my mind, it's ay of x. X is I should do I for I in range. For I in range, and then I, because I is an index, I for index, and then az avg of I, and then I need a global variable, g earth, which is 9.81, okay? G earth, okay? All right, so this is, so let me see if I can comment this, like extract ax, ay, az, okay? And then here, I'm going to, what am I going to do here? I'm going to convert to g's, okay? I can get rid of these semicolons. Sorry about these comments. Don't actually need those in there. Gx, gy, and gz need to be, ooh, that is an interesting point. Okay, so I don't actually know the units. I'm going to comment all of this out. I don't actually know the units of gx, gy, and gz, so I'm going to make a new figure and plot the gyro average, and that is in units of question mark per second. And we're going to plot, we're going to change all this to gx, gy, and gz. So I guess it's finally time to plot the gyro data. The question is it in degrees per second or is it in radians per second? We're going to know real quick when we plot this data. Okay, so there's the gyro data. All right, so right there, that is like 5, right? Now, here's the thing. If this was in degrees per second, 4 degrees per second is absurdly slow. Now, 4 radians per second, that's hella fast, okay? So this is definitely in radians per second, okay? So that's radians per second. And that green line is GZ, which means this thing is just spinning like crazy. Which is funny because, like, it's just chilling on the z-axis, but it's definitely, like, it's rotating about that axis. That's wild. All right. Enough chatter. Let's play. All right. So we can uncomment this now, because now we know that the gyro data is in radians. Okay, we don't have a gyro offset, so we can't do that. If ax, ay, and a 0 are not 0, well, obviously that's not true. We compute the reciprocal norm. Okay, so I've never understood why they do this in C. I'm just going to do np.square root, and then instead of doing times equal, I'm going to do slash equals, and basically that is going to normalize the accelerometer measurement. Okay, so that's that. So we've normalized the accelerometer measurement, and now we estimate the direction of gravity and vector perpendicular to magnetic flux. Okay, so this is the stuff that I don't quite understand, but basically what you're doing is you're taking the current guess of the quaternion and you're computing a vector with that quaternion. And so in the AHRS filter, if you look at the header file, you'll notice that you don't notice. Yeah, right here this is C code, but when the class is initialized, it assumes that the quaternion is 1000, and so it assumes that the quaternion is straight up. Now, or sorry, it assumes that the quaternion is 1000, which means the roll, pitch, and yaw angles are 0. So there's this function that you can convert quat to Euler, and I might have those functions in here somewhere. They're probably in the helper functions, which would be where? Not the modeling, yeah, in the helper folder. And rotation, I feel like there's like some quat to Euler functions, yeah. Quat to Euler, and probably Euler to quat. Where are you at? All the way at the bottom? Jeez, this code. Oh my gosh, how many lines it goes with this? Wait a second, is this a MATLAB routine? Oh, why would you do that? Why would you put it in here? There it is. Uh-oh, I'm gonna sneeze. Okay, I'm back. Yeah, shoot. Okay, so here's quat to Euler, and then there's probably Euler to quat. Okay, yeah, so we can use those two helper functions to go back and forth. Now the question is what do we think the sensor is doing? What do we think the roll, pitch, and yaw angles are doing when it's turned on, right? And so this is where I'm having trouble, right? So the sensor is flat, and gravity is down, and it's measuring that. So z is almost 10. So yeah, so I think we should just initialize the quaternion. So init quaternion, and say q0 is 1, q1 is 1. And actually these need to be vectors, by the way. So we need to do like 0 times ax average plus, no, and then q1 is 0 times ay, well, ax average. They're all the same length. q2 is, and I'm going to say this is q0, that's fine. q2 is 0 times ax average, and q3 is 0 times ax average. And then what I'm going to do is I'm going to say q0 of 0 is 1. Okay? So it's, Euler angles of 0, 0, 0. Then over here, what I need is I need to grab q1 of I, q3 of I, q0 of I, q2 of I, and basically just put i's everywhere. q0 of I, q1 of I, q2 of I, q3 of I. Remember, I is the index in this loop. q0 of I, q0 of I, and then there's minus 0.5. That f is going to throw an error in Python, and then q3 of I, and then q3 of I. Okay, then we do this like cross product error. So half ex is ay times this. So basically what this is doing is ax, ay, az is an accelerometer vector, and that has some vector component. And then the quaternion has another vector component. So basically the quaternion is where you think you're pointing, and then the accelerometer measurement is where it actually is pointing. And then it takes a vector average between those, and it tries to nudge it that way. So here's some integrator windup. If 2ki is greater than 0, according to, I'm going to need this. This is Euler to Quat, right? Can you go away? This is Euler to Quat. I need Quat to Euler. Where's Quat to Euler? This is Quat to Euler. This is it right here. Oh boy, what the heck? Norm. Oh boy, I don't know how this works. Like, can I just, where's the MATLAB version? That code is probably better. MATLAB. Dude, I don't even know where this would be. 6DOF? Probably in the 6DOF folder. 6DOF. Did that get moved to aerospace? Yeah. Makes sense. Euler to Quat. That's Euler to Quat. What about Quat to Euler? Boom. Haha. Okay, this is what I wanted. Quat to Euler. So I'm going to borrow this for later. Throw this down here. Okay, we'll borrow that for later. And then I want to open up the AHRS filter in FastKit. And where are you at? You're in hardware, IMU, AHRS. And 2KI is 0. Okay, and then 2KP is 2. So remind me of that. Okay, so 2KI is 0. So it says if 2KI is greater than 0, which it's not, so it's not going to do any of this. So integral FB is all 0. So I'm just going to get rid of all that, okay? Then we apply proportional feedback, okay? So it says GX. So this is supposed to run, this AHRS filter is supposed to run in real time. So what we need to do is we need to say GXI, or GXI is GX average of I, GYI is GY average of I, GZI is GZ average of I, and then what we do is we say GXI, GYI, and GZI are 2KP, and 2KP is 2.0. And so basically the accelerometer vector and the quaternion vector are different. So what it does is it nudges it. So it takes the current gyro measurement and adds that like nudge and nudges it over. And then we integrate, then finally we integrate the rate of change. And so we say, I don't understand why that didn't like go where I want it to. Maybe this one's in the wrong spot. Okay. And so we're going to say GXI, GYI, GZI, and we need, and so that's going to be times equals, and then we get rid of the F's because it's, you know, what's that called? It's already a floating point. We need the elapsed time, which is going to be the time t of I minus time t of I minus 1. So obviously this is going to throw a hissy fit unless I do 1 and minus 1. Yeah, I don't know what else to do. Okay, and then we set some common variables, QA, QC. Now I don't, you know what I want? This is fine. This is fine, everything's fine. So I'm going to say Q0 of I, Q1 of I, and then Q2 of I. I still don't understand why they do like QA, B, and C. Like, why didn't they just leave it as, I mean, again, I didn't write this AHRS filter. There you go. Okay, and then Q0, and then it says plus equals. What I would rather do is say Q0 of I plus 1 is equal to Q0 of I plus, and then all this stuff. So QB is fine, GX it needs to be at I, QC is fine, GY is I, and then Q3 needs to be of I. This is kind of terrible programming here because I'm using like indexes in some places and not in others. So now we're going to say Q1 of I plus 1 is equal to Q1 of I plus, and then QA is fine, GXI, QC is fine, GZI, Q3 of I, oh dear, GZI, and then we've got Q2 of I plus 1 is equal to Q2 of I plus QA. Dude, when I do this, like, I really have no way to debug this and see if it's right. Like, I'm just going to have to keep going. Like, until we, like, I get, like, better, like, what I need to do is get like a box with an accelerometer in it and like hold it flat and throw it in the air, make sure it stays flat, and then catch it in my hand and then run it through this code and make sure like that works. You know what I mean? Because this is, I have no really way to test this. Maybe I'll do a follow-on video after I test this. I don't even know if this YouTube video is going to be, you know, beneficial for the general community, but I don't know. Maybe it'll spark some interest, and maybe some people will be like, "Whoa, what the heck is a quaternion?" You know, and I'll be like, "Dude, I don't know. Go watch another YouTube video on quaternions." Like I still don't really know. I just sort of work with them. So it looks like I have to normalize the quaternion. So I'm going to say I plus 1 here now, and then I plus 1, and then I plus 1. And then since we're doing this a lot, let's copy that. Copy, paste, paste, paste. It's like we're in kindergarten again. We just copy and paste. All right, and then here we do the same thing. This is I plus 1, which I just copied, but this is slash equal because this is really a norm. And then we're going to go copy slash, and then copy, oops, slash, and then copy slash. And then that is it for the entire loop. So let's see if that runs and doesn't throw a hissy fit. It looks like everything's good. So we should be able to now convert the quaternions to Euler angles. So those Q0, those are vectors, right? Yeah, so I should just be able to say roll is np dot atan 2 of 2 times Q0. I just need to get rid of these dots because that's a MATLAB thing. 1 minus 2, and then squared is a star star. And then I need to get my parentheses right. So that's right, and then there, and then that's it. Okay, and that's the roll angle. Oh, I need an equal sign. And I kind of want to multiply by 180 over np dot pi. Maybe not. Let's leave it. Let's leave it in radians. Okay, so then theta is np dot a sine 2 times Q0 minus Q3 Q1. Get rid of that semicolon. Get rid of that. And then, oh wait, I'm doing roll pitch yaw. So this is pitch. And then yaw np dot atan 2 Q0 Q1 times Q2. Get rid of this. Get rid of the dots. Change the squares to stars. Okay, and then we should be able to plot PLT to, oh, let's copy and paste from up here, this guy. Yeah, beautiful. Okay, and we should be able to do Euler angles in rads. Okay, and we'll say roll, pitch, yaw, and then change this to yaw, pitch, roll, and then the last figure should be roll, pitch, and yaw. Oh, that's a gyro average. Oh, it's not below. Where's that PLT dot show? It's right there, but there's probably a PLT dot show up here. There's 2 PLT dot shows. This PLT dot show needs to be after profit. Okay, let's see what we got. Blast. NumPy has no attribute atan2? How did it just throw that error now? Is it arctan? Huh. Okay. I didn't know that. So this must be arcsine. There you go, figure 5. Oh dear. We broke it. Q0? Wait, what's going on here? Close, Q0? What the what? What the what? Uh, didn't I like take Q0 of I and then do Q0 of I plus 1? I don't understand. And then I did Qi plus 1, Qi plus 1 over here. I see. You just start at 0, and then you go to I plus 1. Okay, I'm getting some craziness. Whoa. What the what? Oh my goodness. What did we do, guys? Q0? Nan. Oh no. Everything broke. I thought we did the recip norm. Oh, dang it. No, we didn't. The whole thing went unstable because we forgot to divide by the right number. Maybe now? Oh, yes. This looks awesome. Okay. We are going to legend because I keep forgetting. Oh my gosh. Let's see. Dude, that looks awesome. So pitch. See, it's interesting. It's almost like it thinks it's upright maybe, and then pitch is 0, and it's just like spinning around in circles here. I wonder if it's on the launch pad for a long time, right? I wonder if we should wait a second. How did when we did the elapsed time, how did that work? Yeah, because that's a negative, like I minus 1 ends up grabbing them. That's why I did that. Oh. I think what I'm going to do is I'm going to do this. Plus 1 and then I. See that. See if it doesn't throw an error. Doesn't look like it does. Okay, cool. Okay, there we go. Yeah, so there the initial, I ended up doing like time of 0 minus time of minus 1, which is like the last data point, and so it made it like a crazy negative number. This makes me feel a lot better. So the IMU accelerometer is flat, and then it starts doing its nuts, and it's like after it deploys the chute, it just goes crazy. Okay, I don't know if it's right, but that one's done. I did the code. Okay, number 5. Take the body frame acceleration vector and transform it to the inertial frame. Okay, so here's the thing. So AX, AY, AZ are in the body frame, and we need to convert it to the inertial frame. So we need to say for I in range, again, 0 to len of AX, AVG, okay? And we need to say AX is AX, AVG of I, AY is AY, AVG of I, AZ is AZ, AVG of I, and then what we do is we create an A body frame, which is NP array of AX, AY, AZ, right? And then we need to grab the roll angle, well, I'm going to call it R, is roll of I, and again, that's in radians. Pitch is pitch of I, yaw is yaw of I, and then we need to make a transformation matrix. And that, I think I have Python code for that. So I should just be able to grab GitHub, probably Aerospace, and then probably 6DOF. But there's probably a Python script in here somewhere. Yeah, 6DOF.py. Is there like a TIB matrix in here? Because that would be very cool. Yeah, there's a TIB. Haha, this is what I want. Wunderbar. I'm going to grab this. Okay. Alt-W. Now, how does TIB work? Okay, so F, that's in the, these are in the inertial frame. Oh, see, I transpose it. Okay, yeah. Yeah, see, this UVW is in the body frame. You multiply by TIB, you get the inertial frame. So that's what we're going to do. So we're just going to copy this whole thing. Kinematics. Copy. we're going to go, bam. I'm just going to paste that in there. Okay, and then we're going to have C theta, C psi, SV, S theta, C psi, S psi, T theta, TIB, and then, so theta is pitch, psi is yaw, phi is, well, wait, can't we just, so I'm going to say phi, theta, psi, and then there's some cosine functions. Here's the TIB matrix, and then we're going to say a I for inertial is equal to np.matmul, TIB matrix, A, B. And then we say AX B of I is A I of 0, and then AY of BI is AI of 1, AZBI is AI of 2, and then we need to make empty vectors for a, what did I call it? X, B is 0 times AX AVG, and copy that 3 times. Y, Z, and then I guess I didn't need to do that. A, Y, A, Z. Okay, and then we can plot. So again, we make one more figure, and we, forget the gyro. The gyro, we just use the gyro to get the gyro is just a means to get the Euler angles, because we're going to integrate those. See, we technically already integrated the gyro to get the Euler angles, and then we took the acceleration vector in the body frame and now we're converting it to the inertial frame. And so this is going to be the acceleration inertial, and this is going to be AX, AY, Z, and then this is going to be AX, B, 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 and then, so the last plot here should be, oh gosh, should be this. So that's the inertial frame. See, this is so freaking cool, dude. I don't know if you guys remember, but see, here is on the launch pad, and there's a positive 10 here, and then on the other end, there's a negative 10 here, right? But that's because the IMU flipped upside down. But the freaking attitude, the AHRS filter figured it out and flipped it around. Man, that's freaking cool. Okay, so now here's the thing that I forgot to add, and number 5.5 is subtract gravity inertial. Okay, so I'm gonna do that like up here, because all we need to do is just subtract G Earth. Okay, from so the last figure should be, oh my gosh, that's so cool, dude. Man, I love it when something comes together. That's freaking cool. Okay, now we double integrate, okay? And then we profit. All right, so double integration. First we need velocity. So Vx is 0 times Ax average. No, B, no. Wait, why the heck did I call these B's? These are I's. Dude, is it that late? I'm getting sloppy. Again, I have no idea if the scientific community here or the YouTube community is going to appreciate this video, but look, if you see something and you're just like, dude, Dr. C, that looks cool, make another video about that. That's what I want you to do. I in range 0. If you're even still here, this is a long video. I have no idea how long I've been recording, but it feels long. Okay, so I'm going to say Vx of I plus 1 is Vx of I plus Ax of I times elapsed time. And I'm going to do a minus 1 here, right? And I'm going to say elapsed time, which is really like a dt. I'm doing Euler integration, by the way, if that's okay with y'all. Time t of I plus 1 minus time t of I. I think that'll do it, right? So let's do that 3 times. Vy, Vz, Vy, oh gosh, Vy, Vz, and then we just need to change this to Ay and Az. Okay, so if we did this right, that initial spike, we should see a spike in the Vz velocity, right? The vertical velocity. So this is Vx, Vy, Vz, and this is, oh, I gotta change those B's to I's, because it's inertial, acceleration. And this is going to be a Vx, Vy, Vz. And then this is not acceleration inertial, it's velocity inertial. And it's not meters per second squared, it's meters per second. All right, so remember, the acceleration vector got truncated, okay? So the acceleration vector got truncated, but how high? Ooh, that's pretty terrible. Where's VZ? Vx, Vy, Vz, Vx, Vy, Vz. Oh. Come on. Come on, give me something good, give me something good, give me something good. Yes! Yes, this is terrible, but hey, this is what you get for cheap IMUs. Okay, so the accelerometer is saturated, so it did increase, and it thinks it's going, 50 meters per second, which there's no way, right? It is a huge rocket, and then this is when it started to fall, and it looks like it's falling at minus 90 meters per second, which honestly may not be incorrect. It's totally possible. The only way to make this better, really, it would be to get a better accelerometer that didn't saturate under launch. You logged data faster. I don't know how many data points we have, but I don't think it's taking data fast enough. I think it needs to take data at like 1,000 hertz if it could, or maybe like 100 hertz. Anyway, let's integrate one more time and get position, even though it's going to be garbage, but let's just do it again just because. That's what we said we were going to do in this video. Px, Py, Pz. Px, Py, Pz, Px, Py, Pz, and then instead of AXI, we're going to do Vx, and then Vy, and then Vz, and then here we're going to do not velocity inertial, but position. So we should see it climb, and then you're going to see what happens with the saturation. It's going to go up, and then it's going to go through the ground, like really quickly. So this will be X, Y, Z, and then we'll have Px, Py. I guess I could have just done X, Y, Z, but it's fine, PZ. And there we go. So figure 8 is going to have what we want. Yeah. I mean, whoa. What the heck is that? So, I mean, our rocket went in the air, right? But 200 meters is like 800 feet. It went way higher than that. And then, according to this, it hit the ground here, but that's impossible. And the reason why is because it's saturated. So it didn't predict how high it went. But this is the best I can do with the data that I've been given. So there you go. Like I said, I hope this sparks some interest. This code probably needs to go, let me grab desktop. Let's see, plot, post-launch analysis, launch, not notes, the data. This probably needs to go into the aerospace folder. Do I have like a rockets, spacecraft design, rocket seminar series, open rocket? Maybe I should I'll just start making a folder on rockets. Why not? I'll start putting stuff in there. All right, so I'm going to push this code, and you guys can do what you want. You can do what you want with it. Maybe you'll learn something about quaternions, about transformation matrices. Who knows? If you want to hear more about the specific thing, just let me know. Added, launch, post, analysis, code, git push, origin, main. All right, folks, it's on the internet. I hope you enjoyed this video. Hope you have a good night. Post in the comments if you have any questions.